So to state the claim I want to prove is that we have something like this. We have a product of two Gaussians. So we have this Gaussian times another Gaussian. So the Gaussian of random vector z with expectation h times x and covariance r. And then the other Gaussian has x as its random vector, and it has expectation h bar, x bar, and p bar. Okay? So then I want to show that this is the same as a product that looks like this. A Gaussian in z with expectation z bar, covariance s bar, times another Gaussian in x with expectation x hat and p hat. Now I'm going to spell out just in a moment the details of what all these hat and bar quantities are. The main point to observe here is that I've sort of factorized this original Gaussian, or this product of Gaussians, so that now I have x only in one of these Gaussians. And that is useful. We like to factorize things. And then it was the details. So I have z bar is the same as h times x bar. Then I have another vector, x hat is the same as x bar plus a matrix w times z minus x hx bar. So that was the vectors involved in it, and then the matrices are first I have matrix S, which is the same as R plus H P bar times H transpose. And we're going to have a matrix that we call W, this one, which is P bar H transpose times S inverse. Finally, a matrix P hat, which is identity matrix minus W H P bar. And of course, most of you can probably recognize that in this you see all the things that are in the measurement update of the Kalman filter. So basically we want to prove the Kalman filter now. And we're going to do that in 3 steps. So in the first step, I want to look at the factorization of PDFs and see how the possibilities of factorizing a PDF in a marginal and a conditional can be used to tackle this. Then in the second step, I'm going to deal with all the matrix algebra that results from that. And in the third step, I'm going to look at the results that we previously derived for marginalization and conditioning and sort of recognize what's going on here as fitting together with those theorems. So I start with step 1. So an important point I have to understand that as a completely general result, you can factorize a PDF P of z and x in 2 ways. P of z given x times P of x, which is the same as P of x given z times P of z. So see that here we have something that is of this form, and then we're going to move it over to something that is of this form that possibly will fit what's up there. So we identify these terms with what we have here. So I define this joint distribution P of z x by saying that P of z given x should be my first portion. And P of x should be the second portion. So that's then I define a unique PDF. There is only one PDF that will satisfy this. So then I'm ready to go on to step 2 and work with this thing. So this thing is given by quadratic form. Because everything here is Gaussian, or Gaussians are given by quadratic forms. So then what I need to do is just to manipulate that quadratic form. And that quadratic form looks like this. X minus x bar transpose p bar inverse x minus x bar. And then I have from, so that was from this one, and then I have from this one, I have some additional stuff. When I multiply the Gaussians together, so then I add the quadratic forms. Now I want to sort of stack this together in a single vector and eventually get a single covariance matrix. So my first step towards stacking this together, I can do like this, x minus x bar, and then I can take the same vector, z minus hx. And then I have a matrix that is a block diagonal, because these two quadratic forms are sort of happening independently of each other. But I'm not really satisfied yet, because still I have this x in both here and here. I would want to separate x from get it in only one of these slots, and then I need to do some manipulations. So let me just state first how I achieve that. So this is the same, I'm going to show that in the limit. It's the same as x minus x bar, z minus hx bar, times identity matrix minus h transpose 0 identity matrix, p bar inverse 0, r inverse 0, and then I need transpose of these things. There should be a transpose here, and yeah, I forgot those transposes. So the transpose of that, then I get the minus h down here and a 0 here, plus I, and then find x minus x bar, p minus hx bar. And now you'll notice that here I have, this is very similar to this, but suddenly it's z minus hx bar instead of c minus hx. So how did I get that? Well, if I look at this last part, let me see if I attack this, if I end up back here. So this works because I minus h and I 0 times x minus x bar, z minus hx bar, because I work on this. And then I just do algebra. So for the topmost one, it's just I times x minus x bar, which is x minus x bar. For the lowermost one, I have this h times x minus x bar, which gives me minus hx plus hx bar. And then I have identity times this, so I get z minus hx bar. These hx bars I can cancel, and I'm left with x minus x bar on the top, of course, and z minus hx, which is what I have here, and then I've shown that I can get here. Then I've sort of done all I want to do with these outermost vectors, but I have 3 matrices in here, and I would very much like to reduce that to just one matrix. Then I have to do some additional steps, which are fairly straightforward. To do the two steps first, I have x minus x bar, z minus h x bar. Now I kind of want to stack these together into something that I can, when I invert it, end up there. Then it's going to be looking like this. Again, x minus x bar, z minus h x bar. So how does that work? Well, when I start inverting this thing, then eventually at some point I have to reorder the matrices. When I this should be up. When I invert this matrix, I end up with this. It's a standard rule for inversion of block diagonal matrices. And now it just remains to multiply all of that together. So I get x minus x bar again, z minus h x bar. And then I have I times p times a, so I have p bar there. Then I have h times p bar, h p bar. And then I have the opposite here, p bar h transpose. And I have h p h transpose plus r, the whole thing inverted, and x minus x bar, z minus h x bar. Okay. So now it's time for step 3, and then I make identifications with what I had for marginalization and conditioning. Now, if you look at the textbook for that theorem, I have something I call x that corresponds to this x. So I write it like this. Then I have something called y there. That corresponds to my z now. Then I had something called a. That corresponds to my x bar. I had something I call b. Corresponds to my h x bar. And something called pxx. This corresponds to my p bar. And something called px y. Corresponding to p bar h transpose. And finally, that's something called pyy. Corresponding to h p bar h transpose is r, which is the same as s. And then I use formulas for conditioning. So then I get then x hat should be the expectation of what we have in the conditional. With those formulas, this should be the same as a plus pxy, p by y inverse, y minus b. And that is the same as x bar plus p bar h transpose, which is like s inverse, z minus h x bar. I immediately realize that this is what I call w, And then I have my result for the expectation of the last Gaussian. I also need to obtain its covariance, which I call P hat. And this should be the same as P bar, or let me write this again, sorry. Let me write this first in the notation I had from the conditioning theorem. Then it was Pxx minus Pxy, Py inverse, Pxy transpose. This is the same as P bar minus P bar H transpose. And then I'm not going to write S either, I'm going to write H P bar H transpose plus R, the whole thing inverse. Yeah, actually it doesn't matter. Could have written S, doesn't matter, but anyway. So again, this thing is W. Continue here. That is the same now as P bar minus WH, P bar, which is the same as I identity minus WH, P bar. So then I have the covariance. Then it follows from this, that the quadratic form. It becomes is Z minus Z bar transpose S inverse Z minus Z bar plus X minus X hat P hat inverse X minus X hat. And then I'm done because I have identified that this thing on the left now is the same as the Gaussian given by this quadratic form. Of course, this is essentially first and foremost a derivation of the Kalman filter, but it's not only that this is a more general result in some sense, because not only do you have this Gaussian, but you also have that Gaussian that can be very useful for assessing how good your measurement is, which is useful in parameter estimation, in target tracking, and consistency analysis, and many other applications in sensor fusion.